Assalamu alaikum wa rahmatullahi wa barakatuh. Professor Gathia, the president of IUPAC, Professor Ayman Saleh, vice president of graduate studies and research at Ain Shams University. Good morning, ladies and gentlemen, respected guests of the scientific community, worldwide and in Egypt, dear colleagues, dear students. A very warm welcome at the premises of Ain Shams University that is hosting the 5th African Conference on Research and Chemistry Education. This venue, the iHub, has been particularly chosen because this building fosters innovation. This conference is listed on the UN event series with the International Year of Basic Sciences for Sustainable Development in partnership with UNESCO and is endorsed by IUPAC, the International Union of Pure and Applied Chemistry. On behalf of the organizing committee, I would like to thank our sponsors, Dragon Oil, IOP Publishing, Taylor & Francis, and Praxi Labs for supporting this event. A special thanks goes to Dr. Ashraf Badawi, CEO of IRIS Events, who was responsible for all the logistics of this conference, like meet and assist, flight and hotel bookings, audio-video at this venue, and a lot more. Thank you so much, dear Dr. Ashraf. The rest of the organization, like daily communication with the speakers, gathering the booklet information, the presentations, and the bios, all this has been done by the listed organizing committee members of the booklet. I would like to put special emphasis on my student, Manar Mustafa. Can you please stand up, Manar? This is my right hand, and she is really doing a great job. Thank you so much. And Dr. Hussein Farid, who actually established this logo of the conference. I would like to thank the chair of the scientific committee and the chair of the conference in particular for this marvelous interaction with you, for this opportunity to host this here. And therefore, I would like to ask Professor Nadia Kandil now, the chair of the scientific committee, to give her welcome remarks. Thank you.
Good morning. Thank you, Ghada, for the introduction. Dear Excellency, Professor Ayman, welcome, and our guests. It is my pleasure to welcome all of you to this unique gathering that we gather once again in the 5th African Conference on Research in Chemical Education and with distinguished professors of chemistry education experts from Africa countries and various countries of the world to participate in the conference and activities to emphasize the growing role of chemistry education for sustainable development. The theme of the conference is Teaching Chemistry for Sustainable Future, reflects a growing recognition of the power and the importance of a chemical education for African societies. Sustainability goals, such as climate change, is one of the greatest challenges of our time, and its adverse impacts undermine the ability of all countries to achieve sustainable development. Chemical education as integral part of the overall educational processes need to emerge for the 4th industrial revolution, which embeds the balance between chemistry through education and vice versa. Thus, chemical education must gear our efforts to innovation. The African countries' STEM education to develop the human resources quality for the technologies of the 4th revolution, international revolution. I would like to thank Professor Farouk Fahmy as the chair of the conference, and Professor Ghada, of course, she is do everything, and Dr. Ashraf Badawi, who do all the best to have the conference as distinguished one. Thank you for the organizing committee and all members of the organized and the scientific committees, and special thanks to the plenary keynotes and all oral speakers and all participants to have this conference such a distinguished form. I wish you all a very fruitful, successful conference and a nice stay in Cairo. Thank you.
I would like to invite the chair of the conference, Professor Amin Farouk Fahmy, who is here, to give his welcome remarks. Please do.
Good morning, everybody. You are highly welcome in Egypt, in a sunny weather and sunny environment. So it is a good time in Egypt, November and December, before the rain and cold, and you are experienced. The Excellency Professor Ayman Saleh, Vice President of Ain Shams University, and His Excellency Professor Garcia Uyupak, President, dear distinguished guests and colleagues, it is a great pleasure for me to welcome you all to the 5th African Conference on Research in Chemical Education, held under the main theme, Teaching Chemistry for Sustainable Future. CRESIA 5 is hosted by Ain Shams University, by Egyptian Academy of Science and Technology, and the International Union of Pure and Applied Chemistry, Federation of African Societies of Chemistry, and 10 Academy Falconese, and sponsored by IOP Publishing and the Dragon Oil, Praxi Labs, and Taylor and Francis. The previous 4 conferences were held in Ethiopia the year 2013 in Ethiopia. The second was in South Africa, November 2015. The third one in Algeria, 2017. And the fourth one in Nigeria, September 2019. Dear distinguished guests and colleagues, the conference is intended to act as a platform for enhancing chemistry education for preparation of new African citizens who are able to deal with international global challenges for sustainable future. To this end, educators, we are as educators and researchers at all levels are invited to share their our vital knowledge about systems, for example, system thinking and impact on the fourth industrial revolution, and chemical pollution and its impact to the global climate change. So also we are invited as indicator to be engaged in the recent innovative teaching and learning strategies like project-based learning, inquiry-based learning, STEM education, systemic-based learning, SATLC. Dear distinguished professors and guests, in spite of the current war and the world financial crisis, a diverse group of speakers from different places of the world actively participate in the conference. There will be plenary, keynote, and workshops presentation given by eminent experts from appropriate fields of research on chemistry education. Distinguished guests and colleagues, I hope that all of us attending Acrisia 5 will gain innovative ideas for promotion of chemistry education and its role in the systemic sustainable future. I would like to thank keynote and the speakers beside panel and workshops organizers for their efforts to make this success of the conference. Also, my thanks goes to sponsors, organizing and scientific committee members, and their chairs, Professor Ghada and Professor Nadia, for their invaluable help and the efforts of organizing and this successful conference. Also, my thanks go to Ain Shams University for hosting the conference and for strong and continuous support that help to make the success of this conference. Also, my special thanks goes to His Excellency Professor Ayman Saleh and Professor Garcia. Finally, I would like to offer my thanks to Dr. Ashraf Badawi and his group for his big efforts in organization of the logistics of the conference. Also, I wish you all a successful and fruitful meeting, and I hope that you will enjoy your stay in Egypt. Thank you.
Thank you, dear Professor Fahmy. I would like to invite Professor Ayman Saleh, the Vice President of Ain Shams University for Graduate Studies and Research, to give his welcome remarks. Please.
Bismillah ar-Rahman ar-Rahim. Good morning, everybody. I would like to start by welcoming you all, distinguished professors, experts, colleagues from all over the world. We are honored to have the African international bodies, speakers, organizers, and attendees from 18 countries sharing their knowledge in chemistry and aspirations and dreams for a better future through environment preservation and sustainability. Part of Ain Shams University strategy and policy is to create a strong scientific network with both African and international colleagues. Although our gathering is all about chemistry, I want to talk about something else, but relevant, about giving hope for the younger generation. In a world tormented by economic and political crises, dedicated scientists and think tanks with moral integrity are our hope. During the last few years, there was an increasing boost to basic sciences at Ain Shams University, as well as nationwide, with many initiatives like Science Up, like STEM schools, and increased funding by the Egyptian Academy for Research and the Egyptian Authority for Financing Science, Technology, and Innovation. At Ain Shams University, we encouraged what we called the Scientific Circle for Chemistry among Ain Shams University faculty members, as well as multi and interdisciplinary research. An issue that I hope you find time to discuss is the brain drain of our chemists from Africa to the Western globe. How can they travel to and fro, but remain building their own countries? I welcome you all in Cairo at Ain Shams University, and I wish you a fruitful meeting. Thank you.
The president of Ain Shams University was unfortunately not able to join us in person, but he left a recorded message. So let us all start the recording.
Good morning. It gives me great of sustainability. We have decided to host this important event here in celebrating the essential needs of basic sciences to meet crucial challenges such as universal access to food, energy, health coverage, and communication technologies. Needless to say, that basic sciences are at the basis of major technological advances that stimulate innovation, reshaping the future. Obviously, the global economy is undergoing a transition and huge challenges, given the geopolitical challenges that we are all living, and after 2 years of the COVID pandemic. Current jobs are being automated away, and new jobs are being developed on a regular basis as a result of technological developments. Everyday technical innovations are transforming the way students learn, communicate, and interact. The integrated learning experience and teaching students how the scientific method can be applied to daily life distinguish new approaches from traditional science education. Science is critical to tackle complex challenges for humanity, such as climate change and many others, as it lays the foundation for new approaches and solutions. How can science best fulfill this commitment to society? How can we create dynamic connections between knowledge and action? These concerns have led to a new approach, which is sustainability science adopted by the UNESCO. With our contribution to the community in Egypt, Africa, and the whole globe, we are bringing together key stakeholders from the academia, policymaking community, and specialized institutions in order to better define and broaden the term sustainability in science. Sustainability science focuses on the dynamic interactions between nature and society. The last decade has witnessed the emergence of an array of increasingly vibrant movements to harness science and technology in the quest for a transition towards sustainability. The sustainability science approach is essential for effective decision making with regard to global sustainability, since social, environmental, and cultural systems are closely linked. Chemistry education takes a particularly important role in an era of post-pandemic. The pharmaceutical and chemical industries have changed a lot in the recent decades. Has chemistry education kept up? In particular, and in terms of drug delivery and vaccines, we need to raise many questions. What skills are industry looking for now? Are universities and high schools meeting those needs? What do students need to do to be competitive in the chemistry workforce of tomorrow? We at Ain Shams University will continue with our partners to support efforts to educate and advocate the development of science in general and chemistry in particular. This conference is a powerful reminder of the complexity of the challenges the world is facing and the immense responsibilities this creates for us as educators. We hope by the end of this conference that we can come up with recommendations that will foster better educational tools and methodologies. With this, I would like to thank you for your valuable contributions and wish you a successful conference and an enjoyable stay here in Egypt. Thank you very much.
Thank you very much. Now to our opening lecture, Professor Garcia. Professor Javier Garcia Martinez is a professor of inorganic chemistry and the director of the Molecular Nanotechnology Lab, a world-leading research center working on the synthesis and application of nanostructured materials for the sustainable production of chemicals and energy at the University of Alicante, Spain. He's the founder of Rive Technology, a technology-based company that commercializes nanostructured catalysts that significantly reduce CO2 emissions while increasing energy efficiency. Professor Garcia is the president of IUPAC, and he received many awards in entrepreneurship, like Emerging Researcher Award in 2015 and Catherine Haag Award for Entrepreneurial Success in 2018, the American Chemical Society Awards, so many different awards, and he's a member of the Council of Emerging Technologies at the World Economic Forum. what I really like to emphasize also on is that he's an alumni of the Global Young Academy, and this is how we met, and we became very dear friends. So thank you for being here with us, and the floor is yours for your opening lecture, please.
This is not next slide. Okay. Shalom alaikum. Good morning, everybody. I'm delighted to be here, although my team lost yesterday. God and I were in Al Khalili when Spain was out of the World Cup. I'm really delighted to be back in Egypt, actually to be back in Africa. I was in Cape Town very recently in the International Conference on Chemistry Education. It seems like Africa is at the center of chemistry education, so I'm delighted to be here. So, esteemed authorities, dear friends, ladies and gentlemen, I want to start by quoting Nelson Mandela, who once said, "Education is the most powerful tool we have to change the future." And that's what we are doing here today. We are changing the future through education. I want to start by saying thank you to my dear friend Gada and also Nadia for putting together this fantastic and very much needed conference, and all the volunteers, all the young people around the room who is making the magic happen. So with that, I would like to start by saying a few words about what we are doing now at IUPAC to foster sustainable development through education. So this summer has not been like any other summer. I hope you still remember how hot it was during this summer. We reached all-time record temperatures in the northern hemisphere, not only very high temperatures, but also droughts that cause fires all around the world. Just to give you a sense of how bad this is, only this year, 3 million hectares have been destroyed because of the fires all around the world. And at the same time, we are having these huge fires. We are having also floods everywhere. And the recent one in Pakistan is just going beyond comprehension. Just to give you again a sense of how big these floods are these days, the amount of land that was underwater in Pakistan is 3 times the size of Portugal. So it's this unique combination of extreme weather conditions, droughts, floods, which put in a lot of pressure on the environment and actually, to be honest, on our ability to secure the future for the planet and to put food on the table for everybody. And since we are in Africa, I want to emphasize that this continent, despite its low contribution to greenhouse gas emissions, it remains as the most vulnerable continent. And this is really unfair. I mean, this is how we are treating our planet. Some countries are contributing a lot, and others are suffering the consequences. That's just not sustainable. Here, some data in terms of how climate change is affecting Africa. This year we are celebrating the 30th anniversary of the Climate Summit in Rio de Janeiro. I was there just a couple of weeks ago. Remember this important occasion. And as you know very well, actually we are in Egypt. Just a few weeks ago in Sharm el-Sheikh, you were hosting the COP27. So 30 years of trying to fight climate change. And the reality is that we are failing to do so. We failed at least 27 times. We have not been able to reduce greenhouse emissions, greenhouse gas emissions, and this is really sad. And actually, after having so many leaders here in Egypt, they left without the ambitious agreements that everybody was demanding. There is a very clear demand from everybody around the world from our leaders to our leaders to get to these agreements, and they are failing us. And let me show you just a picture of one of the reasons I think they are failing us. This is the pictures of the leaders, of those leaders meeting in Rio de Janeiro 30 years ago, and now the leaders meeting here in Egypt just a couple of weeks ago, 30 years later. Who is missing there? Half of the population. Where are the women? They are not there. Our leaders are failing us, and they are not representing us properly. I wish we would have more female world leaders, because definitely this is not sustainable also from a societal point of view. And chemistry has a lot to do to change this reality. But in order for chemistry to contribute to a more sustainable future, we need to fundamentally reimagine chemistry. Small improvements in catalyst efficiency, or just not using solvents, or reducing our dependence on oil is not going to change this big picture. We need to rethink chemistry in a big way. Let me show you now what I think is the best picture of the chemistry enterprise these days. I know it looks very complicated, but it's actually very simple. So every single year, we take from Earth 1,400 million tons of oil derivatives, more than 500 million tons of reactants, and 250 million tons of water. That's everything we extract from the planet. All these arrows you see there is everything we study and we teach here in universities. Fischer-Tropsch, Haber-Bosch, Michael addition, Fidelkraft acylation, all those chemical processes. And then, at the end of those arrows, what we produce. The sad news is that only 31% of what we extract from Earth is actually converted into useful products. And for that 31%, only 8.6% is recovered. That is not sustainable. We cannot keep producing in this way, because the planet can just not tolerate it. When I became president of IUPAC, Gevante Chemie asked me for an opinion paper on how I see the future of chemistry. I entitled that contribution Chemistry 2030, a roadmap for a new decade. And let me start from this very simple reaction, which is the way we think about and we teach chemistry. A plus B to produce, to yield C. How many times we have seen that in different forms. The main problem we have is that we have become so good at producing C that we are dying of success. We are producing too much of chemical products. And it looks like in the way we teach chemistry, we think about chemistry, that once we produce C, then it's not our problem anymore. And it is. We are the ones producing all this wood. And we are not doing that, putting sustainability at the beginning of the conversation. So instead of thinking, teaching, and implementing chemistry in an extracting kind of way, taking from Earth and then using and emitting, we need to learn from nature. Nature operates in cycles. Do you remember from your high school years, the cycle of water, the carbon cycle, the phosphorus cycle? And that's the only way to move forward. Just imagine if every single tree that grows on Earth, it will be piling up instead of being recycled as new nutrients for the Earth. And that was my proposal, to think of a new kind of chemistry where once we produce C, that can be a raw material for a new cycle. Of course, many of you can be thinking already, okay, Javier, that sounds like a nice academic idea for an editorial, but that's even possible? Yeah, it is possible, and actually there is a lot of nice research being done on what I call circular chemistry, which put sustainability at the beginning of the design of molecules and processes. And this paper published in Nature Chemistry is a very nice example of that, because these authors deal with these very difficult plastics which are almost impossible to recycle, but they introduce these dynamic bonds, that's how they call it, in the structure of the polymers. So with a simple acid washed, they can disassemble the monomers to take the monomers back, and you can see here some vials of how they polymerize the plastics, extract the monomers, and made the plastic once again. How they have been able to produce these new kind of plastics? Having sustainability in mind from the very beginning. So when they design this plastic, they put in the structure of the plastic something so it can be disassembled and reused again. That is not how we are operating these days. If we look at the structure of any given polymer, and this is a good example, high-density polyethylene, you will imagine that there is nothing in that chain of monomers that will allow for recycling. It's the opposite. Every plastic we have around us has not been thought to be recyclable, but actually to last forever. That's why it's so difficult to recycle these materials. So again, these authors published last year in Nature a fantastic paper, when in this case they introduced these breakpoints. Again, something in that molecule that will allow for disassembling these plastics and then getting the monomers back and producing the plastic again. Why I want to highlight these two studies during my talk? Because these are excellent examples of how now researchers are thinking of molecules and processes with the recycling in mind from the very beginning. Now we try to recycle everything as best as we can. But again, those materials has not been designed for recycling. And the best example of that is in every pocket in all of you, is your cell phone. We all know that we have many elements from the periodic table in our cell phones, which are very scarce. We have cobalt, thallium, tungsten, all these, of course, rare earths. And do you think your cell phones have been designed to be recycled? Do you think it's possible to recover those scarce elements? It's almost impossible. That's why all this e-waste, all this electronic waste is shipped to Africa, countries like Ghana, to Nigeria, when they just melt all this electronic waste to try to get some elements back. So that's my proposal, to include sustainability in the way we design molecules and processes, and of course, that means a new way of teaching chemistry. I was mentioning climate change at the beginning of my talk, and I want to introduce now, I only have time for one example, but this example I think is very inspiring of a way that chemistry can significantly contribute to fight climate change. Early this year, a group of scientists, actually engineers, from the TH in Zurich, introduced this very nice new technology published in Nature with a very attractive title, Dropping Fuels from Sunlight and Air, in a way that is reminding us, at least to inorganic chemists, that sounds a lot to us like the fixation of nitrogen. We have some German colleagues here. When we talk about air and creating products, of course, the Both-Haber process comes to mind. And this is actually a very smart idea. These authors use these photoreactors, which are coated with xenon oxide. This xenon oxide, when exposed to very high temperatures, it loses oxygen from its framework. And then when you reduce the temperature, these metal oxides have a lot of affinity for oxygen, so it can extract oxygen from CO2 to produce carbon monoxide and from water to produce hydrogen. And once you have syngas from air, you can use the Fischer-Tropsch process to produce all kinds of hydrocarbons. Simple idea. From air with solar light to produce fuels. And actually they are doing that at commercial scale. You can see some of that fuel obtained in this solar plant actually in Madrid. These people are now using these solar concentrators, these mirrors, to heat that photoreactor to remove the oxygen from the xenon oxide, and then in the other window, which is not shine, then the xenon oxide is now taking the oxygen from water to produce hydrogen and from CO2 to produce carbon monoxide. With the syngas, again, these people are producing aviation fuels just from air and sunlight. Amazing. Something that it looks impossible. And not only at lab scale, but as you can see, at commercial scale. Actually, they founded a company to commercialize this technology. And imagine if this can be done from the 400 ppm of CO2 present in water, imagine what this technology can do with a much highly concentrated flows of CO2 and water. But if there is a big revolution, if there is hope in what science in general and chemistry in particular can do to fight climate change, I want to highlight some recent developments in artificial intelligence. Artificial intelligence in science discovery is the elephant in the room. Let me start with this paper that I think it should be in our textbooks. It should be in our textbooks because this Nature paper published 3 years ago is the Turing test for chemistry. Let me explain. A group of scientists invited another group of organic chemists in a double-blind test to propose synthetic routes for the production of very complex molecules. And again, in a double-blind test, independently, they also asked computers to produce synthetic routes to the production of the same molecules. Independently, a third group of chemists were unable to distinguish which of those synthetic routes were proposed by machines and which ones were proposed by humans. That's exactly the definition of the Turing test. And what is even more surprising is that when these chemists reproduced the synthesis proposed by machines, those synthetic pathways were not only more efficient, but more elegant and with a less impact on the environment than the ones suggested by humans. To be honest with you, this is not even surprising. Why? Because machines are very good at taking into account millions of papers, considering every single data published on the synthesis of these molecules. And we humans, we have our own biases, and we can remember just few set of chemical reactions. So they are much better at predicting, suggesting synthetic pathways to producing all kinds of chemicals. The authors of this paper, this seminal paper, were so aware of the importance of their contributions that in the outlook they wrote something which is written in a language which is not common to scientists. It looks more like poetry. Let me read just a couple of sentences from that outlook. They want to equip machines with the means to learn autonomously from the rich history of chemistry. Once again, these scientists want machines to learn from the rich history of chemistry so they can help us create solutions for the problems we are facing. That's really a vision. And scientists from all around the world accepted that invitation, and they equipped machines to learn from the rich history of chemistry. And computers were reading millions of papers, chemistry textbooks, and patents to learn from the rich history of chemistry. Some of you may think, okay, Javier, I give you that machines can mine papers, maybe read papers, but no way they can learn, they can understand chemistry. Let's think about that more carefully. Because just a year after that seminal paper was published, a group of scientists asked machines to organize all the chemical elements as a function of the chemical properties. If machines are able to understand chemistry, they could organize the chemical elements based on the chemical properties as a function of every single paper we have published. And these are the results. Here on the left, you have the periodic table of the machines. Some of you may be thinking, okay, Javier, but that's not really a periodic table. That's just a bunch of colorful points. Let's give machines a chance. Let's see if we, as an independent group of chemists in a double-blind experiment, believe that machines have understood what chemistry is all about. They were very good at identifying the halogens. And actually, they organized the halogens as we do. Fluorine, chlorine, bromine, and iodine, and astatine very far away. They were also very good at identifying the alkaline metals very far from the halogens that you would expect. And they are reminding us that hydrogen maybe shouldn't be in group 1. You see how far is hydrogen from the rest of the alkaline metals? And we can all think of reasons to have hydrogen very far from these metals. And then, of course, they were able to identify the noble gases. And they are far from the alkali metals and from the halogens. No problem with that. And then we come to my favorite group in the periodic table. I don't know how many inorganic chemists will be here, but they will share my passion. Elements in group 13, very difficult group. And then we all realize how different is boron from aluminium. We keep telling our students that elements in the same periodic table, they share same chemical properties, but we know how different boron is to aluminum, to the point that we invented excuses and give them pompous names like head of the group effect, or the diagonal effect, or inner part effect. Just excuses for things that doesn't work in our periodic table. Look at how different are the elements of group 13 for machines. They are more honest. In a way, they are saying boron is more similar to the other semi-metals than to the elements in their own group. And of course, we have the elements that form diatomic homonuclear molecules that share many similar properties. They were very good at identifying all these elements. And of course, the radioactive elements. And we need to admit we cheat in our periodic table. We use different colors to highlight radioactive elements, because to be honest with you, technetium is much more used because of its radioactive properties than for the properties itself with manganese and rhenium. So I'm not proposing to change the periodic table, but I hope that through this journey through the periodic table of the machines, you have been convinced that actually machines understand what they are reading, because they are able to organize the elements based on the properties in a way we can make sense of. That's huge. That is huge. And now, if we believe that now machines understand, and forgive me for using understand in a very broad sense, I'm aware that they don't understand in the same way we understand, but actually they can interpret the data correctly. How artificial intelligence can help us to build a more sustainable future. So, with those two papers in mind, a group of scientists published this year this fantastic paper. It looks very complicated. It's very simple. Let me tell you what they did. They identify all the molecules we don't want, all the waste molecules, from solvent recycling, from plastic recycling, waste from the drug industry, from lignin degradation. All of these molecules, we have too much of those. Either they are waste or they are very cheap. And then, what do you think they ask to machines? How we can build high added value molecules from these waste molecules. And this is what machines did. They took all these waste molecules and produced some of the most expensive, most difficult to make pharmaceutical molecules in a way that is not only highly efficient, but actually the authors are scaling up and trying to commercialize, as you can see in that pilot plant. I don't know who is going to own the IP of these recipes that has been proposed by machines. But this is a fantastic example of how now artificial intelligence is helping us to identify efficient pathways to go from waste to high added value molecules. Again, this is huge. Machines are telling us how we can transform waste molecules into the most difficult to make compounds. And now people are scaling up that technology. Okay, I hope with that I give you a sense of the limitless possibilities we have in front of us, but I want to tell you a few things about how IUPAC is fostering sustainable development and helping in this transformation of rethinking chemistry in a big way. And nothing what I told you today is a small improvement in efficiency. Nothing what I told you today is saving a little bit of solvent. It's a profound change in the way we think about chemistry, either by introducing sustainability in the design of molecules or processes, using artificial intelligence like other sciences are doing, like biology is really ahead of us in the use of artificial intelligence. And now how IUPAC is helping here. The first thing I want to tell you, and this is a great opportunity, and I hope all of you feel invited, the International Year of Sustainable Development of Basic Sciences for Sustainable Development is a great opportunity for everybody to put science and evidence-based decisions in the front line of the agenda for achieving the Sustainable Development Goals. This International Year is the first time where all the international scientific unions and science academies are joining efforts to create one single message. Science is vital to create a more sustainable future, and there are many different opportunities to do so. A few years ago, actually during our centenary, we created an interdivisional committee on green chemistry for sustainable development, aware of the importance of green chemistry in the future of our profession. With interdivisional committee, what we wanted to emphasize is that everything we do within our committees, within IUPAC, needs to be thought, designed, and implemented with the perspective through the lenses of sustainable chemistry. This is a great effort, and I'm really grateful to everybody involved in this committee who are helping us to put the Sustainable Development Goals in our agenda. They are doing that by organizing conferences. I was very pleased, and Gada was also there to see the impact of what we are doing or what we are fostering in terms of green chemistry. We attended the IUPAC International Conference on Green Chemistry with hundreds of scientists who are really putting green chemistry at the front end. So this is not a nice to have, this is a must have. And they are very clear. Paul Anastas was there, and there was a very clear vision on the future of chemistry. Again, the main message was small changes are not going to fix the problem. But I want to emphasize here today KenRound, not only because we have people from this committee here, because of its long history of tackling world needs through chemistry. A couple of examples here. The one that I feel more inspired by, and actually I already mentioned this in a way, is the fantastic conference workshop that they organized in Nigeria on the issue of e-waste in Africa. Yes, an image here of how we are dealing with electronic waste in the world that is completely unsustainable. That's a shame. You know, we shipping our waste to Africa without any safety, where people are just melting our cell phones and computers to get tiny amount of metals in a very unsafe manner. I'm mentioning this conference here also because now there are follow-up IUPAC project. You can see the date is August 2022, and this is creating effective teaching tools and methods to learn about e-waste. This is fantastic. I'm really happy that Francesca, the chair of KenRound, is leading this effort. So we learn more about e-waste, and we are putting these learnings in our teaching materials. Fantastic IUPAC project. So thank you everybody involved in this project. I'm also very pleased to tell you that early this year we launched a new initiative, the Global Conversation on Sustainability. And this is just an opportunity for everybody to engage in a local conversation on sustainability, because one thing which is very clear is whether sustainability is of course a planetary problem, it needs to be solved at local scale. And that's why we are inviting everybody in their own universities, local schools, town halls, synagogues, mosques, churches, whatever, to have a discussion, a panel, a presentation about sustainability. This has been a fantastic experience because people are not afraid to talk about what the environmental issues is. Maybe water, is air pollution, whatever is their local problem. And these conversations are a starting point to address those issues at local scale. And of course, this being a conference on chemistry research, I want to say a few words about how IUPAC is leading the future of chemistry education, what we are doing there. The first thing I want to say, since we have the chair of CCE here, and that's, I shouldn't say, but that's my favorite committee. I'm being involved with CCE for more than now 15 years since I joined Division 2. I'm being a Division 2 representative in CCE. And this is not only the most active committee in IUPAC, but probably the most inspiring. And this mega project, because it's not only one single project, but many projects together about system thinking, is really changing the way chemistry is taught all around the world. And just to give you an example, and that's very unusual in an IUPAC project, we have 5 task group chairs, just to give you a sense of how big this project is. In a nutshell, and you know much more about system thinking in chemistry education that I know, but just to give you my 2 cents on this new way of teaching chemistry, is by breaking the silos in the way we introduce chemistry concepts. So we usually limit the way we teach chemistry about maybe structure, reactivity, properties in a very, very narrow way. Students will be lucky if we connect one specific topic with another within the same subject, but it's very rare that we connect the theme of the day with our planetary boundaries, with the impact of what we are explaining on our quality of life, on the environment. And system thinking is a wonderful opportunity to put chemistry in context. As I said, this is having a profound impact on how we are teaching chemistry, and this is just a fantastic example of the kind of impacts having. This article in Nature Sustainability, we rarely get papers published in Nature, and this is one of the many papers that the IUPAC people and our collaborators have been publishing in this top journal to explain how system thinking for education can really change how we think about sustainability. Again, this, for the ones of you who want to learn more about system thinking in chemistry education, my own knowledge on this topic is from mainly this review article, an excellent review article in Nature Reviews Chemistry by some of the people who are leading this effort. They are great. They are doing many things to inform the community about the potential of system thinking in chemistry education, and this whole issue of the Journal of Chemical Education is devoted to system thinking. Again, plenty of resources for the chemistry community to learn more about system thinking and the way IUPAC think about this. And again, if you can see the title of the first paper, Can Chemistry Be a Central Science Without System Thinking? So this is a fundamental rethinking, reimagining of chemistry education. And I'm very grateful to Peter Mahaffey and his team in Canada, because they are not only leading this transformation and helping us with all these publications, but also creating these beautiful applets, this beautiful website to connect planetary boundaries with chemistry education. Again, this is from the IUPAC website, and this new tool that connect planetary boundaries and system thinking through this really nice tool. For the ones of you who have not used it, I strongly encourage all of you to play with this tool. Is open, is free, and is actually very, very useful. And now, just again, 2 cents on how IUPAC is doing many things beyond chemistry nomenclature. Because yes, I'm aware when I say IUPAC, this is what comes to your mind, right? Our color books on nomenclature, in this case, organic chemistry, and what we teach our students, how to name things. And that is very important. Actually, I keep saying people that from the beginning of our science with Lavoisier in France at the end of the 18th century to the first third of the 21st century, our science was without a common language. That was a major barrier for the development of chemistry. For most